when we do the acoustic design for a space, we're concerned with or we should be concerned with the acoustic requirements of the users, not just meeting the performance requirements that are prescribed. So the obvious thing that users need in a classroom, for example, is speech intelligibility. They need to be able to hear what's being said. We know that controlling the background noise is very important, and that relates to the building services, but probably more importantly, to the noise generated within the room. How do we explain that? How do we quantify how that's going to be affected by the room acoustic response? Something which we think about less often is the acoustic comfort of the talker when we don't have the benefit of microphones. Obviously, for rooms, the primary acoustic or physical descriptor is reverberation time. But this is really a descriptor of the room physical response rather than correlated with what users actually want. We have STI, and it was great to see the equations there in the last presentation, because that shows you how complicated STI is. So trying to understand the influence of one thing or another on the STI parameter by design is very complicated. And it also mixes up the room acoustic response with the background noise in one parameter. So we can't separate out the effect of the background noise on the room acoustic effect when we're trying to think of speech intelligibility if we use STI. So this is partly why clarity is so useful. So how do we characterize rooms then? And as Trevor mentioned earlier this morning, usually we're not so interested in the speech intelligibility for the person who's close to the talker. We're interested in what are the conditions like for the person at the back of the room. So if we set the distance between the source and the receiver to be the length of the longest side of the room, what we find is that clarity is independent of room size and is only a function of reverberation time for the normal sorts of reverberation times that we get in rooms. Strngth tells us immediately about signal-to-noise ratios. So if we know that someone is talking with a normal voice of 60 dB at 1 meter and the background noise is 40 dB, then we know we need a strength of 15 dB to get a signal-to-noise ratio of 15 dB. So this graph shows the minimum reverberation time with room area to get a value of strength of 15 dB at the back of the room. So when you reduce the reverberation time from 0.8 seconds to 0.4, the reduction in strength is 6 dB. So with classical theory considerations, we might think if we halved the reverberation time, we would reduce something by 3 dB. But if we think about strength in this way, we can see the effect on reducing the noise levels. Strength, however, and we find this in all our measurements, correlates with the amount of absorption in the room and not the reverberation time. So it turns out that reverberation time is a poor descriptor for loudness in the room, and we're actually better determining it from the amount of absorption in the room. They're very simple models. We can understand the effect of any of the parameters on them. And we can understand because they're associated very directly with users' needs about background noise, about loudness, speech intelligibility.